The presenter is Ran Su. He is a senior researcher at Microsoft Research Azure. His main research areas are cloud and AI infra. Before joining MSIA, Ran received his PhD from Tsinghua University. Okay, please start. Okay, this paper got the Best Student Paper Award. Yeah.
So,
please.
Yeah. Hello, everyone. Thanks for the introduction. So today I'm talking about our paper Miniature, which is a fast FPGA-based network simulator for large-scale AI network simulation. So for the audience, you may not familiar with the term miniature. So I just show a short video which I took in the Netherlands this year. So actually, I visited a miniature world in Netherlands, and actually, you can see this term that perfectly describe our intention to build such FPGA-based simulator, which we use specialized circuits that can run with a minimal overhead to mimic the real behavior of a very large-scale system. Oh, sorry. It seems it's not the latest version. Maybe I can just try my laptop. So sorry for the delay. So actually, I have two versions of the slides, and I use the other version. So sorry. So there's a very high demand of the network simulation. So the reason is that for our infrastructure guys, we need to investigate the infrastructure performance. But for the AI guys, they are competing the GPU resources with us. For us, there are multiple scenarios that we need to run on the infrastructure, including we are searching parameter space for better AI framework performance, planning new clusters, and also improving the infrastructure, including collective communication and transport layer. However, it's very costly to run on a real test bed. So the simulation has become a cost-efficient way for studying AI infrastructure. And the core of it is a network simulation, which dominates the simulation time of the whole AI system simulation. And improving the discrete event simulation, or DAS in short, is the kind of focus of this area. And the reason we need DAS is that it provides packet level fidelity, which it is very important to make the end-to-end simulation with high fidelity. And you can see that there are multiple papers on the top conference recently, so it is a very hot topic in this field. And we just do a study on one of the latest DAS, which is Unison, and we use it to run a 1K factory topology with running the tree-based already simulation. And we have two findings. The first one is that for CPU, it's quite inefficient to process network simulation. We found that actually the simulation can be over 2 million times slower than the real time for the simulation. And if as Unison is already a very good simulator that can scale out to multiple threads, and we try to add 64 threads to this simulation, and we found that we cannot scale linear to multiple threads. And we finally got 32 times speed up with 64 threads. But you can see that around 50 threads, we cannot get higher performance even if we add in more CPU threads. So that makes such software-based simulation have an upper bound. And such upper bound is about 85K times slower than the real time. So it is impossible for us to do the large-scale simulation based on software in terms of time and money. So we also did a breakdown of the overhead, and we found that with the increasing number of threads, actually there are two overheads are increasing. The first one is the synchronization overhead between threads. Although Unison did a great job at reducing the synchronization overhead, there is still little synchronization overhead, but such overhead increased much at the large number of threads. And the second overhead is for the computation. With the increasing number of threads, we found that the computation efficiency actually drops. And the reason is mainly due to cache contentions. And here we just summarize the limitations of software-based simulators, including inefficient network processing and also the high event coordination overhead due to the virtual timer, and it's inefficient to scale. So our intention is that can we build a miniature world on the FPGA where FPGA can provide a specialized circuit which can be much more efficient than the software-based one. And also those events happens in near real time to minimize the event processing overhead. Also for FPGA architecture, it's naturally parallel so that we can achieve linear scale out. And I won't talk about the detailed architecture design of this as the audience are from the network community. And here I mainly talk about how we scale our simulation to support a real large-scale AI network. So after we optimize all the implementations on the FPGA, we found that we can only fit around 1,000 nodes into the largest FPGA on the world. So our solution to these problems, we provide two solutions to it. One is multiplexing, which we enable context switch on the FPGA. And here the context switch is it's not the same as in the software, as we only need to switch data but not computation. This is not like the software where we do context switch, we switch both data and computation. This is because the data center has a symmetric topology where we can just, let's take the bottom right figure as an example. So if I first simulate the left part on the FPGA 0, and then I can switch to FPGA 1 without need to reconfigure the specialized circuit, but we only need to switch those states in that circuit. And we can use the minimal link delay as a switch time to avoid any raising condition in such simulation. And we achieve the tiered multiplexing using both FPGA on-chip DRAM and off-chip DRAM. And another scalable solution is that we provide scale-out through inter-FPGA communication. And we can naturally hide the inter-FPGA delay as if we divide the network into multiple parts. Those packets need to send across links, and we also need to simulate the link delay on these links, and this link delay is naturally aligned with the inter-FPGA delay, so that's why we can easily hide it. But both these solutions have drawbacks. Actually, they can affect the performance. For multiplexing, that DRAM bandwidth will become bottleneck, and we found that it is lucky that the latest Xilinx FPGA has HBM, and we found that using HBM can greatly mitigate the issue, because it's still costly to do the multiplexing, and I will show in the result that multiplexing can dominate the computation, the total runtime. And for scale out, the limitation is that inter-FPGA bandwidth has actually becomes a bottleneck, and the current consumer-grade FPGA does not provide very high inter-FPGA bandwidth. And this issue happens even if we only transmit the minimal packets header fields. And another cause of it is it actually requires a large number of FPGAs. But we found that actually these two solutions are friends, not foes. That is, we should use as much as FPGA to get the optimal performance. That is, for example, if we want to, the network can be fit into 16 subgraphs, but we only have 4 FPGAs, then we should use them all and use the multiplexing degree as 4 to achieve the best performance. And here I show some preliminary results. So the first is that we implement the basic endpoint and switch feature, and we found that actually we can fit around 500 endpoints and 20 switches on a single FPGA. And we also find that the implementing network protocols like PFC on FPGA are super efficient. As you can see, the required logical resources are much smaller than the basic node features. And this result actually compares if we want to run a very large scale GPU cluster which has 65K nodes, and we made the performance and compare different bottlenecks, and we find that the multiplexing is the bottleneck for a small number of FPGAs, and inter-FPGA bandwidth is actually the major bottleneck if we have 8 to 1,000 FPGAs. And we have infinite number of FPGAs, then the computation is a bottleneck. And also we find that even if with a single FPGA, we can have over 4,000 times speed up compared with Unison. And also we can achieve even 5 million times speed up if we have 2,000 FPGAs. Yeah, so here's the conclusion. So we analyze the software-based DAS has a speed upper bound. It's due to the slow single-thread performance, and also it cannot scale linearly. And we provide Miniature, which is a FPGA-based AI network simulation, which can scale through multiplexing and scale out, and it can be much faster than the software-based simulators. Yeah. Thank you. I'm happy to take any questions.
Okay, time for one question.
Just one.
Just one.
Only one. Good job, Shuren. I remember around 10 years ago, whenever in Microsoft is the first cloud provider, asked us to integrate FPGA in their servers. And I'm kind of curious about what did you use for those FPGA used in the cluster in Microsoft Azure?
At first we use it, but actually we found that the FPGA in Azure is a middle end one without HBM. Then we turn to use some latest FPGAs with the HBM, and those FPGA platforms are actually available on Cloud Labs. So we vision that we will future open source this project, and people can use Cloud Lab to run such simulator.
It's okay.
Okay.